Welcome to today's webinar on durability and reliability post-processing from rail operational data. Our presenter today is Nicholas Cias. Nicholas is an applications engineer for HBK and focuses on nCode solutions for understanding fatigue and durability and ReliaSoft solutions for RAM studies. He has been with the company more than 10 years and is based in France. Nicholas, it's all yours.
Today's presentation will discuss how operational data can be used to improve the durability and reliability of your products. Obviously, this is a very broad topic. We have 15 minutes to cover it, so I do my best to present a number of case studies and applications while not fully going into the details of each one. So if any question or need for more information, I'd be happy to discuss after the presentation. But first of all, why is this interesting? Why should we talk about this today? And this is actually a growing need for our customers because the rail industry is mainly using national and international standards, and they tend to be conservative, usually leading to over-design of the equipment. And this would be fine if the industry was not becoming more and more competitive with high customer expectation and increasingly demanding life and runs targets. So there is a need to optimize the design and maintenance strategies. And to do this, engineers need to understand customer usage, which is where operational data is actually very useful because they can get you as close as can be to real-world usage. The overall HBK solutions address both the need for data collection and data analysis and management, and more importantly, how each one can interact with the other. And the applications we will discuss today will be illustrated with the Prenscia products, which is the software branch of HBK, the right part of this graph. For the left part, for the test and measurement part, if you haven't looked at them already, would recommend you to watch the previous webinars of this series. I've demonstrated the measurement solutions that we can offer at HBK for the rail industry. They're available online at hbm.com/webinars. So the software solutions that we provide at Prenscia are actually used for the whole life cycle of the equipment. In the design phase, where we discuss customer usage understanding and safety analysis, such as FMEA. In the test and validation phase, where our software can design accelerated test specification, validate them with virtual testing on finite element model, and provide a wide range of signal processing techniques for test data analysis and reporting. And finally, in the operational phase, where we can optimize maintenance strategies regarding availability or cost, or simply monitor your assets based on health indicators. This life cycle is, of course, some kind of looping process. And today, we will focus on how this operational phase can be used as an input of the two first ones. So let's start by defining what operational data means, because this term actually covers a number of data sources, such as the human expertise actually from the maintenance technician on the field, which can directly fuel your FMEA process and risk analysis. It's also the maintenance data and warranty claims, which means all the repair and replacement times, the inspection and failure analysis results that you can collect on the field, which can fuel your reliability studies. And finally, all the time series measurement that you can collect from onboard sensors and which will be an input for durability analysis. These time series measurements can include in-service loading like force, acceleration, or stress, but also things like weather conditions, because external factors like temperature or humidity can actually play a role in component life. Using this data from the field actually raises a number of challenges, and the first one is for sure data quality. So before doing any analysis, always make sure to have a first pass of data cleaning. For example, maintenance data often lack information. Like we know that a component has been replaced, but we don't know what was the failure mode. So things like a fracas system is usually a good practice to turn your raw data into a clean failure mode database before further analysis. For time series measurement, quality issues are more like spikes, noise, or even a complete loss of signal. So in this case, you will want to apply anomaly detection or signal prediction techniques, something that nCode software is particularly good at. So let's now focus on durability analysis examples first. And in this field, damage is the keyword, because in durability, you will want to compute percent of damage generated by a mechanical stress on your structure. And since you want to know this mechanical stress, the stress that is seen by your equipment in order to calculate damage, then the systems you already have on the field turn out to be the perfect source of information. If you can collect the loading history on a set of instrumented assets, you can use this information to calculate the actual damage of your fielded components, as illustrated here with this process where the measurement gotten from the field can actually be played on a finite element model to assess damage or safety factor from this operation run. This is useful if the finite element model corresponds to your actual component to see the actual damage seen by your equipment. And this is also useful to just test a new design and see if it's performing better. Operational data can also give you a clear understanding of customer usage. For example, what kind of maneuver or what kind of ground information is causing the most damage to your structure. I have a look at this GPS trace, for example, here. I can see that I have a zone that is more damaging than the others on my track. So I might wonder, how is this? Is this a bridge? Is this a railroad crossing? Or is it just a cold temperature zone? With such data, you can not only identify damaging events, but also how often they are met within a month or within a year of operation. And all of this actually helps you to build a mission profile, which is a great input for next design studies or test specification. And also, this data can just be used for comparison with what you actually applied for your test with your current standard. I mentioned that these numbers tend to be conservative because they tend to overestimate the load that can be seen in real world, just like this example here. But actually, some of them are kind of getting too old and tend to underestimate the load, so that you can get components that comply with a given standard, but still fail in operation. So comparing those two in terms of severity is always a good preventive measure, just to avoid such cases. Another source of data and information can actually come from just real maintenance activities. For example, a dumping machine that aims at compressing the ballast under the rail. The machine has these dumping tines over here that penetrate into the ballast and squeeze the rocks in order to optimize the rail stability. In this case, placing additional sensors can record the required amplitude and force required to compress the ballast, actually enabling you to quantify ballast quality. For this, you can use metrics such as the maximum compressive force, or if I do a cross-pose of both information, calculate the energy through the compressing cycle. And this effectively turns this routine operation that you perform like every 6 months or every year into a degradation monitoring tool that enables you to plan or optimize maintenance action. I also wanted to present you today this customer case study, which is a good example, in my opinion, of how field data can be used to build a fatigue test specification. This customer has a full-scale hydraulic shaker system. So thanks to this, it can test a complete rail car structure. And just like many of our clients, he was looking for a quick load, which was still representative of an actual usage lifetime. The solution that was put in place was to instrument a set of vehicles and put them into regular operation. You can see here strain gauges that was used for damage assessment, and accelerometers that was used to get back to displacements, which was one of the inputs for the test. And the information captured during these months of operation were, of course, fully representative of actual usage, but needed to be compressed in order to accelerate the test. And to do that, we use the fatigue editing module of nCode software that automatically identifies and removes the non-damaging sections of data. It's allowed to reduce the test time by a factor of 10, while keeping the same damage and failure mode. You can get actually further acceleration by playing with the test speed or by generating equivalent constant amplitude signs. If you're interested to see more details, you can find them in our online article. But the main point being here that by following such a process, you can effectively tailor a test specification for durability in order to reproduce years of operation within just weeks or even days. So let's now talk about the reliability. And in this field, reliability, so let's define reliability as a probability that an item will not fail during operation. So now, probability is the keyword because we are talking about a statistical concept. Based on observation of failure times from a sample population, mathematical models like a variable distribution can be used to characterize the probability of failure of any similar component according to usage. So metrics like mean distance between failure or mean remaining life can then be inferred. And this is important because knowing this probability of failure allows for optimized maintenance strategies and spare parts pulled. So a lot of money can be saved with accurate estimations. Well, unfortunately, it's not always easy to test several components in your lab in order to get this input data in the first place. So this is where maintenance and warranty data turn out to be a gold mine, because they contain all the repair data, as you call it, from the field. It indicates when each component failed and how long it took to replace it. So this data can actually be used to more precisely determine the failure rate of each component or specific failure mode. This information can then be like assembled into a reliability block diagram, which will allow for a system level prediction. Metrics such as maintenance costs, or equipment list, and system availability. So because operation data represent a broader population and actual use conditions and abuse conditions actually, it allows for better reliability predictions. At the end of the day, it reduces over maintenance and increases asset availability. However, if you already played with real-world reliability data, you might know that everything is not always clean. Sometimes lacking important information, such as which component failed actually. Or sometimes failures are not just independent because the second push button repair, for example, would actually depend on how good we repaired the first failure. In these cases, it's just not possible to fit a standard variable distribution on your data set because the underlying assumptions are not met. So if you find yourself in such a situation, the good news is that usually it's still possible to move on thanks to other methodologies like reliability growth analysis. This is particularly helpful for fielded systems data analysis. And this methodology can allow you to analyze complete system or subsystem data, like we see here, door failures collected, regardless that it contains different components failure or different failure modes. The statistical process behind will be used in order to still be able to predict the next number of failures that should occur on the field within the next period of time. So keep in mind that depending on how your operational data looks like, not everything will be possible, but there has always been a path we can take in order to extract value from it. And last but not least, actually, it's worth noting that these applications can be either run manually by the engineers or automated. And we have set up systems where new operational data collected every day, stored and labeled in databases, then just used automatically to update component life predictions or health indicators using statistics, signal processing, and machine learning. This is it for today's webinar. A lot more can be said, of course, but we have already seen in 15 minutes that operational data can be key information for the reliability and durability studies, that they can come from different sources that require cleaning techniques before analysis. And since we account for real world usage, they are great input for engineers to optimize the test specification and get more accurate prediction, effectively helping your company to save time and money.